All right, welcome. Today, we are diving deep into the world of kinetic analysis. We're going to uncover the invisible forces that are behind every single movement, from something as simple as a jump to a truly mind-blowing athletic performance. Let's get right into it. I mean, just look at this. It seems impossible, doesn't it? A diver launches into the air and they seem to just defy gravity. They speed up their spin, then slow it right down to slice perfectly into the water. So how on earth do they do that? Is it just raw talent, or is there something else going on here? Well, you probably guessed it. The answer isn't magic. It is pure physics. And I promise, by the end of this, you are going to have a complete analyst's toolkit to see and understand the hidden forces that make these incredible movements possible. We're going to make the invisible visible. Okay, our very first tool is the foundation for absolutely everything that follows. I want you to think of it as the essential blueprint for any kind of kinetic analysis. It's how we can isolate an object and see every single external force acting on it with total precision. It's called a free body diagram, or FBD for short. And the whole point here is to simplify a really complex situation. We strip away everything, the background, the crowd, the noise, and we just focus on the athlete and the forces. It's all about achieving crystal clarity. And putting one of these together is this really logical three-step process. First, you pick your body. Let's say it's a high jumper. Second, you simplify their entire shape down to something basic, like a box or even a dot. And third, this is the most important part. You draw every single external force with pinpoint accuracy. So let's build one right now. So here's our jumper, and we've simplified them down to a simple box. Now, this little box represents their center of mass. That's the single point that acts as the average location of all their body mass. This simple step makes the whole analysis so much easier to handle. Now, let's add the forces. The first one is the one that's always there, no matter what: weight. That's just the force of gravity pulling the jumper down. And on a super detailed diagram like this, we show it as a vector, an arrow that points straight down from that center of mass. It's calculated simply as mass times the acceleration due to gravity. And here it is, the force that makes all the action happen, the ground reaction force, or GRF. This is literally Newton's third law in action. The jumper pushes down on the ground, and the ground pushes back up with an equal and opposite force. This upward push is the key. It's what allows us to accelerate, to jump, to move at all. And just like that, our force blueprint is complete. So we've got our static blueprint. It's a great snapshot in time. But how do we turn that snapshot into the full story of the jump as it happens over time? How do we get from a simple diagram to dynamic, explosive motion? Well, let's grab our next tool and see how this all builds. It all kicks off with incredibly detailed data. See, an instrument called a force plate can measure that ground reaction force hundreds, even thousands of times per second. When we plot that super precise data against time, we get this, a force time curve. This is the raw, detailed signature of the entire movement. Okay, this is where it gets really, really cool. Using Newton's second law, we can literally transform this force curve into an acceleration curve. If we take the net force, that's the ground reaction force minus the person's body weight, and divide it by their mass, we can figure out the exact acceleration of their center of mass at any given instant. And the story just keeps unfolding. By integrating that acceleration data, which is really just a fancy way of saying or summing up all the changes over time, we can generate an equally detailed velocity time curve. So now we can see exactly how fast the jumper's center of mass was moving upward at every single moment. And here's the final step in this beautiful cascade of information. We integrate the velocity data one more time, and that gives us the displacement time curve. And this graph right here brilliantly shows us the final result. The very peak of this curve tells us the exact height the jumper's center of mass reached. So get this, from one super detailed graph of force, we've derived the entire story of the jump. Okay, so we have our data, we have these incredibly detailed graphs, but what does it all mean? How do we look at a bunch of spiky lines on a chart and actually understand what the athlete was doing? Let's learn how to read the story that these curves are telling us. So, the most important thing to understand is this one simple comparison. When that ground reaction force is greater than the athlete's body weight, the net force is positive, which means their center of mass accelerates upward. It's that simple. And when the GRF is less than body weight, the net force is negative, and they accelerate downward. This is the fundamental rule for reading these graphs. And what's amazing is that different movements create these unique patterns or signatures. For walking, the vertical GRF has this classic double peak shape. That first peak is your body absorbing the impact of your heels striking the ground, and the second peak is you pushing off with your toes. But for a jump, you see something totally different. A little dip as the athlete unweights themselves, followed by one enormous peak that sends them flying. The shape of the curve literally tells the story of the movement. All right, we've pretty much nailed linear motion, up and down, forward and back. But what about that diver from the beginning? What about the spin? It's time to add the final and maybe most complex tool to our kit and really tackle rotation. You see, rotation isn't caused by a simple push or pull. It's caused by something called torque. The easiest way to think about it is as a twisting force. It's what you get when you apply a force at a distance from an object's center. This is exactly what athletes use on the ground or on the diving board to generate all the spin they're going to need for their entire time in the air. Now, this is one of the most elegant and beautiful principles in all of biomechanics. Once an athlete is airborne, there are basically no external torques acting on them. And what that means is their angular momentum, which you can think of as their total amount of spin, is conserved. It stays constant. So, if their total spin is constant, how in the world do they speed up and slow down? And this right here, this is the secret. It's absolutely brilliant. They can't change their total amount of spin, but what they can change is their moment of inertia. That's their body's resistance to rotation. By pulling their arms and legs in super tight into a tuck position, they decrease their moment of inertia. And to keep that angular momentum constant, their rotation speed has to increase. Then, to slow down for the landing, they do the opposite. They extend their limbs out, increasing their moment of inertia and slowing their spin right down. It's a masterful manipulation of physics, all while in midair. So there you have it. From the simple blueprint of a free body diagram to that amazing cascade of graphs that turns force into motion, all the way to the principles of torque and angular momentum, you now have the complete analyst's toolkit to look at any movement and truly see the invisible forces shaping what's happening. And that leaves us with one final thought. We've been looking at elite athletes, but these exact same forces govern every single step you take, every time you get up from a chair, every time you jump. So the next time you move, think about it for a second. What story are the forces telling about you?